My name is Daniel Raygoza. I work for General Dynamics Advanced Information Systems, and I'll be talking about automated malware similarity analysis. I'll be the first to concede that that title sounds a lot more complicated than it actually is, I think. The approach I'm going to talk about is fairly straightforward and kind of to the point, and I think it's the simplicity that gives it its strength. So some quick disclaimers, just because I ran into some problems with on here. I'm not here on behalf of anyone other than GD, and none of the work I've done here is anything other than my own, I might say. So the problem I'm trying to address is as we reverse engineers for more in-depth and technical answers, I think we are not doing a very good job of reducing duplicate effort, meaning as teams grow, it becomes difficult to keep track of who's analyzed certain components of code, and trying to find that analysis again at a later point to avoid reanalyzing code is a fairly difficult process. We've done some work, obviously, in terms of sharing information, but I don't think there's any good way to find information for that purpose. So, all right, so the target niche I'm aiming for, and this really isn't, I'm not targeting all malware analysts and certainly not all reverse engineers, but if you work in an environment where you're typically going beyond dynamic analysis, we're going beyond sort of surface analysis, whatever you want to call it, whatever level you want to call it, if you're going and you're unpacking code and you're spending a lot of time analyzing it for implementation details, for characteristics that you can use for intel purposes, whatever the case may be, I think it's really important that you don't duplicate that again just because of how time intensive and expensive it is. So the project I'm working on is not necessarily trying to draw similarity in a vague level, sort of like, you know, trying to find all keyloggers in a set of malware. It's more about finding the tiny bits of code that are similar across, or similar or identical across a whole lot of malware. And I think it's really just a different problem, and it's a different approach than some of the other projects I've looked at. So this is sort of like the spoiler slide of telling you the initial idea that I started working with. And that is to use IDA for auto-analysis of all the samples and break them down into components that can be individually compared, so functions in this case. And I realize there's some problems there, some of you already realize, which is auto-analysis in IDA isn't perfect. It's actually kind of screwed up. But truth be told, like, that's pretty much the best we have right now. And there's some other ways you can address that, and I'll go into that a little bit later on. So then the question becomes, what sort of comparison do you use for all these little function chunks you have? And there's lots of different algorithms you could use. There's fast Fourier transforms. There's sort of like the bin blast approach other people have taken. I've started out implementing a fuzzy hash, and I'll go into what that is shortly, but it's primarily because it was simple to implement and I had decent results. But that's not really where I want to stop. I think we can take all these other algorithms that are applicable to tiny chunks of data and use those to calculate similarity and also expand upon that. So once I calculate similarity amongst all the functions that are components of this binary, I aggregate all those scores into a score for the samples themselves and compare and give them a similarity score based on these little tiny chunks of similarity. So for those of you who aren't familiar with fuzzy hashing, it's essentially hashing but not cryptographically secure. So it produces a hash value that can be compared against another hash value, and similarity scored, it can produce a similarity score between the two of them without having to compare the original data. So it's tolerant of slight changes like truncation, insertions, shifting, and things like that. It makes it useful for sort of tolerating the types of shifts and changes you see in code reuse, because a lot of the times in code reuse you'll see insertions, sliding, and sort of that thing. You don't really get massive amounts of changes in when you run into code reuse. So fuzzy hashing in malware is not new at all. I think there's been several papers on it, and people have been using it for malware analysis for quite some time. But the problem is most implementations talk about fuzzy hashing the entire binary. So when you're dealing with Windows binaries in particular, you have a lot of PE structure. So if you're dealing with small binaries, you typically get a fuzzy hash value that tells you a lot about the similarity between a PE structure in two files, which is not that useful and doesn't really address what you want to know, which is how similar is the code. For large files, usually what you find is they contain an embedded payload of some sort, whether it be a decoy document or a second stage payload, something like that. Again, we're not talking about the actual code in the sample we're looking at. So the similarity scores are not very accurate when you look at them on that sort of level. Some of these issues, but certainly not all of them, are addressed by fuzzy hashing at the function level. And I think that's true of other algorithms as well. If you look at fast Fourier transforms, I think you'd have better results if you applied them at the function level as opposed to the entire binary. And there's some downsides to applying it at the function level. Obviously, I'm not comparing stuff that may exist in other segments that may be important, but I think that's a fair trade-off, because if you're doing in-depth reverse engineering, you're typically doing it on the code, not necessarily the data that it relies upon. Okay, so just going back on some of the papers I've read, and I think you'll find that a lot of stuff that's been written has been dealing with the entire binary as well, with the exception of some of the papers that deal with sort of call tree analysis and looking for leaf nodes and things like that. So quickly to mention some stuff that isn't free that might be sort of related to what I'm talking about, Xenex, BinDiff, and VxClass. I haven't used VxClass, I've used BinDiff. I'm pretty happy with the results. However, it really didn't suit the needs of what I was trying to aim for. And there's also, I mentioned H.P. Gary's dynamic DNA because it's sort of a classification scheme. And I wanted to bring up the point that what I'm trying to develop isn't a classification scheme. So I'm not looking to group pieces of malware based upon their behavior or what type of activity they perform, things like that. That's an interesting problem. It's a different problem, because grouping them in that way doesn't tell me that the code has been reused. It doesn't tell me if they share components. And BinDiff is kind of neat in the sense that it'll tell me the differences fairly well and then presents them in a really nice way. But again, it doesn't tell me in this sea of components what has been reused, what's similar. Huh? What's that? Yeah. Well, there you go. And there's other private tools, I'm sure, that some of your organizations have access to, but clearly something free would be nice for everyone, I think. So the refined idea, after having talked to a lot of people who are really smart and probably smarter than I am, is simply to create, rather than focus on fuzzy hashing of functions, just sort of focus on creating a project that allows us to implement similarity algorithms on a granular level by taking apart the PE file, extracting all the components that are important, and then applying algorithms such as fuzzy hashing to derive a similarity information from it. So some of the limitations. I know my title says automatic, it says automatic in the title, but the truth is it's not perfect, right? So automatic would imply that somehow I could deal with packed executables, which is what most of us deal with. And the truth is I don't have any way of doing that for you. I'm not awesome enough to write a generic unpacker on my own and give it away, but there's a couple of ways of addressing that. One is you might have one of your own. Two is I expect that if you care about this sort of thing, you're already unpacking most of the samples you're looking at anyway. So it shouldn't be too big of a deal. Fuzzy hashing also has its own limitations, and given that it's the only algorithm I have implemented at the moment, it introduces some issues. Primarily, the difficulty of fuzzy hashing is it's not very accurate for small chunks of data. So for functions that are particularly small, you won't get good similarity scores. It's also not aware of assembly mnemonics. So it considers all of those differences and offsets to be fairly significant. So the end result is it's good for larger functions. It's also fairly conservative in its scoring for similarity. So it ends up being that if you get a high similarity score for two functions, chances are you have some pretty good matches. All right, so just mentioning again, I'm not aiming for a classification system. I'm also not aiming for a malware identification system. So at no point would you want to throw something in the system and then suddenly say, well, it has matches to some other malware, so it must be malware. That's not really the goal. I mean, the code that got reused could easily be some like base64 encoder or something like that. And without whitelisting that sort of information, it's not really suited for identification either. So just quickly, the implementation details. It's written entirely in Python, MySQL, PHP for the front end, and it should work on anything IDA works on, really. So the long-term idea in trying to go forward with this is to simply stick to using IDA for the function blobs and extracting all the individual components, feeding all those components through feeding all this data through components that can extract the data we think could be used for determining similarity. And going back to what I was saying before, is if we're only extracting functions, there's other bits of information we can use for similarity analysis, including like the strings, the giant blobs of data. We don't know what they are, for example, and IDA just sort of assumes they're just blobs of data, things like that. And the other component also written in Python is an interface to the database which stores all this information in a structured form. And at the moment, it's pre-computing all similarity information. And the reason it's doing that is one of the issues with fuzzy hashing, at least, is that there's no good way to sort those fuzzy hashes. So searching through them efficiently to try to find a match and get similarity information is really difficult. And if you pass that down to the client, it'd be a really time-consuming process, especially if you have lots and lots of samples. So we essentially pre-compute all the fuzzy hash values, compare them against all the other fuzzy hash values in the system ahead of time, and store those in the database so that queries are fairly fast. And there's also a front-end component, which is right now web-based, and the goal is to make that just sort of abstract so that you can build other tools on top of it. Just some other ideas that have been thrown my way that I'm considering as well is allowing reverse engineers to submit an IDB as opposed to a sample. That way you can fix up any of the problems the auto-analysis has prior to submitting it for the system. And nulling out, at least for fuzzy hashing, nulling out some of the operands so that the shifts in offsets don't produce as much of a difference, so that they're still similar. The other one that I would have loved to bring today would have been like Google's courget. I don't know if any of you read about it. It's sort of a enhanced version of a BS diff or a binary diff between two executables. The idea is that it's aware of assembly mnemonics, so it's able to produce really, really tiny differences between two pieces of code, assuming that they're very similar or different revisions of the same code. So I think in this case, the implementation would have been something like simply doing a courget difference between all of the binary samples in the system and looking for the smallest deltas and considering those the most similar pieces of code. And again, it's a really simple algorithm. It should be fairly straightforward to implement, and I think it would have decent results, similarly to a fuzzy hashing. The other idea that was been thrown around is integrating the results into IDA, OLLI, or immunity, so that when you're doing your analysis in IDA, you can have the similarity score added as a comment to the function or something to that effect, so you can quickly know that as you're going through your IDA disassembly, this function has been seen or something very similar to it has been seen in these other samples. You might want to go check out the report for it or something like that. Again, there's definitely more algorithms to be added. It's just a matter of time and effort, and given that this is something I want to make free, doing it on work time isn't really applicable, so I have to do it on my own time. Otherwise, I wouldn't be able to give it away. So, yeah. So it's been taking a little longer than I would have liked, and certainly longer than if I had time at work to do it. All right, so quickly, I'm just going to show you the process of ingesting some executables in the system, show you some data, and a quick web front end to all this. Great. It'll take a second. I had to rebuild my VM, so this isn't perfect, and I was actually up all night fixing things, but it should still work just fine. So I have a few samples here, just miscellaneous stuff I downloaded off the internet. I had better sample data, but then it was clear that the samples were chosen based upon stuff I know about from doing work operationally that my employer was not comfortable with. So I've downloaded all this stuff off on like offensive computing, so it's kind of junk samples, sorry. So right now the idea is that you just dump as much stuff in a directory, and really I want it to be as non-interactive as possible. So the idea being, like, after you've done your unpacking, copy it to a network share, and eventually a script will pick it up and do all its work and ingest it in the system. So you run this, sorry. Oops. So you would run a Python script to, actually I'll just take an MD5 deep. I think I've already ingested those executables, so it's telling me I'm wasting its time. So the extractor script is responsible for running IDA, allowing the on-analysis to be performed and extracting all the function blobs and any information that's necessary to be stored in the database. I would say it takes about, even on this laptop, it takes about, you could probably do maybe 4 or 5 samples a minute. It's not too bad, but if you get more than that, you might want something beefier than a MacBook running in a VM. So as this is running, it's actually producing these little fuzzballs, what I call them. And the overall project is called Fuzzball as well. It's called Fuzzball because it's just it's a ball of random stuff as far as similarity algorithms go. And that's sort of the goal, is just to be fairly abstract. These little fuzzballs are actually everything we need to store in the database and calculate similarity later on. So the sample itself, the IDB from it, any of the functions, the disassembly output from IDA, things like that. After that runs, I'm assuming that'd be on a cron job or something like that for you for operational purposes. You would run the ingester script, which is responsible for calculating similarity and storing everything in the database. That's also fairly straightforward. It just runs through the zip files, creates all the tables, calculates similarity. It's all fairly straightforward as far as being non-interactive. There's really nothing you have to choose to do. And this is the simple web front end I came up with. And truth be told, I don't really use this as much as I just use straight SQL queries, just because that's what I've gotten comfortable with over time. For future development purposes, all of the actual logic, I would say, is actually SQL stored procedures. So a different front end would be fairly simple. And this front end took no time to write at all, because it was really just calling the correct stored procedures to get a list of information that was useful. So you see all these samples that got ingested in the system. It's just a list of things that are in the system currently. Sample similarity is a link. It shows you all of the similar samples above a certain threshold. So in this case, we see 2 different binaries listed, along with the number of functions that were scored above a certain threshold, and their average similarity, and the overall score. The score is calculated based on the size of the function weighted against the similarity of the function. So if you have a large number of functions that are very, very similar, that score will be a large number of large functions that are very, very similar. You end up with a very high score. So there's no upper bound to the score, but it reflects the raw amount of code that's similar between 2 samples. So if you click on a relationship between 2 samples, I'm trying to find a good one now. Obviously not everything's useful. And in this case, we actually found 2 identical functions at the exact same offset, which for 2 binaries, which isn't really that interesting, but let me see. That's 82% similarity. So this might be interesting. And it's just one function. Again, I'm not going for full out, we're saying these 2 binaries are identical, but just looking at them, just going back and forth, it looks like it's just a simple offset change. So, is this important? I don't know. It depends on what binary you're analyzing. That could be a function that's responsible for a fairly unique crypto implementation you haven't seen anywhere else. That might be important to draw a link between 2 pieces of code. And this is kind of bringing me back to what I was saying before, which is that, again, we're seeing one tiny function in this binary. If you apply a similarity algorithm to the entire binary, you probably end up with a fairly low similarity score. And this would not show up as more than a blip. It would be filtered right into the noise. You'd ignore it because you're looking for the exact matches. But I think these types of tiny matches are more interesting, because they tell you one because if you're dealing with the same actors over and over, if you're dealing with the same people producing code over and over, it helps you build those links that you might miss otherwise. Because if another guy analyzed a piece of code that was a fairly complex RAT that used HTTP as its communication channel and a weird encryption scheme, and I analyzed one that's just a very simple RAT that operated over DNS or something, the fact that they shared the same crypto scheme might be hard for us to figure out. Other than talking to everyone and mentioning, oh, I found this one algorithm, it looks pretty weird. I wrote this Python implementation for it. Does it look familiar? Other than that, there's no real way of doing that, to figuring that out. And I think that these guys aren't necessarily rewriting these algorithms every single time. They're definitely reusing code. So it might be worth looking for these sorts of things. And again, because of the whole sort of political situation, I can't really tell you of particularly good examples, but I can say that I found some pretty interesting stuff that we didn't know was similar before. And there's definitely some code reuse that we're missing. And I really look forward to implementing different algorithms and seeing what sort of results pop out, because I'm convinced that fuzzy hashing right now it's telling us something that's interesting, but I'm also fairly convinced that other algorithms would tell us something different and probably build different relationships that I'm not seeing yet. So I'm being told I'm done. If there's any questions, feel free to catch. Oh, sure.
Two questions. First question, have you tried on polymorphic malware? What results do you get out of fuzzy hashing react to polymorphic?
Right.
Can you repeat the question?
Sure. He's asking, how does this sort of work with polymorphic code? When I typically see polymorphic code, it tends to deal with the packer itself. I haven't seen too much polymorphic code in the actual code that's being implemented, or the code that's being packed. In those situations, as long as the static binary itself even resembles in some fashion the other binary you're trying to compare it against, you might have some luck. But if what you're dealing with is if you're dealing with a packed binary and you haven't unpacked it yet, this is going to fail miserably. I mean, this may work for detecting packers if that's what you were trying to aim for in some circumstances, but I wouldn't expect it to have particularly good results.
Question.
Sure.
If a piece of code was compiled with 2 different versions of the compiler,
Right.
which might,
Right. Even optimization schemes, right? Like the question was, would 2 different compilers produce, or 2 different versions of the same compiler even produce substantially different code? Yeah, absolutely. Different optimizations would too. And in those circumstances, I think the sort of more heuristic approach of some of the other commercial tools might do better at determining similarity. But I'm not so sure that that's really what we're trying to solve with this. I'm not sure it's a solvable problem with this technique at all, really. That requires more of trying to determine what the function is intended to do versus what the actual code is. And I think that's just an entirely different problem that I'm not really trying to address at this moment. Oh.
How do you approach non-malicious library code like Seven, for instance?
If IDA detects as a library code, I ignore it. So if IDA can detect it via flirt signatures or something to that effect, then I'll ignore it. Is that kind of what you're getting at?
Doesn't know about Seven, though, and there's lots of other non-malicious libraries out there.
Right.
Might be so.
Oh, absolutely. Yeah, no, if we're not trying to distinguish non-malicious from malicious code, I guess, at this point. My idea was to support whitelists, so you can ingest entire binaries that you know to be good and assume that any matches against those functions are benign. But at this point, I mean, there's no real sort of heuristic way to determine something is bad or not. And certainly, I'm not so sure that even a whitelist is that fantastic of an idea, given that I mean, there's some libraries that are fairly unpopular, I would say, or fairly unique to certain people or certain groups of people that might be interesting to see similarity in. But I guess it depends on what you want. Anything else? If anyone has any samples they'd like to throw at it later on, feel free. Just drop me a thumb drive. I promise not to steal it from you. Or just stop me, ask you questions, or tell me I suck. That's fine. All right, thank you.